So, hey, hello. I've just been informed that one talk is delayed at the other side, so we're gonna wait for like 5 minutes to start. I'm sorry for that delay. But in the meantime, if you have any question that even before we start, I'll be happy to answer. No? Okay. Then let me ask you. So, any one of you can tell me what are you most interested into the talk? Feel free to answer in Russian. Migrations. Okay.
I want to hear reports about Wikipedia.
Uh-huh. Because you want to use it, or because... Okay. And you want to help people to move to Postgres? Okay, we're on the same page. So, welcome everybody. I was just saying that the one other talk was a little bit delayed, so we're waiting just some final minutes before we start. Apologize for the delay. If there is any question prior to the start of the talk, feel free to shout. Ready? Okay, so hello again, everybody. Привет. That's more or less much that I can say. So let's get started. I want to talk today about the topic that I think it's very interesting for the Postgres world. Even though it talks about MongoDB, I think it's very interesting for the Postgres world because what I'm going to be explaining today is how to use tools that are available in the Postgres ecosystem to help people that are on MongoDB and help them come to Postgres. So I will point out some of the reasons why MongoDB people may want to come to Postgres or may want to come back to Postgres. I won't get into much details about all the things that Mongo may or not be good at, just some of them, but it's not the topic of the talk. So I'm not going to be here bashing MongoDB, although there might be some reasons that few of you probably know about doing that. What I want to point out precisely is how to help those people to come to Postgres for whatever reasons they have. And so, in my opinion, if you're a solutions provider, if you work for a consulting company, if you work for a product company that develops product on Postgres, if you're a user of MongoDB, this might be very interesting because it opens a new market. It opens new possibilities. It opens a way of doing something which is very difficult if you don't have the appropriate tools, but can be done very easily if you find those appropriate tools. And so it opens a new market, and this market is helping MongoDB people come back to relational, or come to, precisely in this case, to Postgres. So this is the idea. I hope that you find it interesting and you can use it in your daily work, and that you can share this opportunity with others, and again, go out of our comfort zone, out of our relational world, out of our Postgres world, and reach out to MongoDB people and tell them, hey, we can help you. Here's our help. So that's more or less the idea. Just before getting started, a little bit about myself and my company. I am the CEO of a company called AK Data. Bonus points for you if you can guess the meaning of the name of our company. And yes, it is related to Postgres. Yes, congratulations. So this is a company where we focus on research and development on databases, which is basically a nice way of saying that we like to have fun doing stupid things, although some of them eventually turn out to be maybe not that stupid. One of those, it's called ToraDB, and I'm going to be talking today about it. And it's a database that brings together the NoSQL world and the relational world, more specifically MongoDB and Postgres worlds. And so it's going to be part of the topic discussion today. Other than that, as a company, we provide solutions on Postgres, support mainly, but also consulting, training. And well, here are my coordinates in Twitter, LinkedIn. Of course, please ask questions here. If you have any further questions later on, let me know. I'll be happy to answer. All right, so this is more or less the planning. So I'm going to talk to you very briefly about some really important MongoDB limitations, at least from the perspective of a relational database user. And then we will study all the available possibilities of how to help these people migrate to Postgres and how to solve that. And then I'll show some numbers. So let's talk about these MongoDB limitations. Again, not limitations per se, but limitations from the perspective of what a relational database user has that MongoDB may not have. So the first one is pretty obvious. Well, it's like not having ACID might be a little bit bitter, right? So in MongoDB, the only way to have transactional semantics is to embed everything within a single document. So, MongoDB has documents look like JSON, and then everything that you put inside a document, like for example, let's say you have like in one example, you have like a cart for a e-shopping application, and then you embed all the product information within that cart. That part, when you modify, when you update, when you insert it, that is atomic. So your warranty safeness. By the way MongoDB does that is with exclusive locks. Theoretically, those are typically fast operations, so concurrency also works, but that is atomic by means of these atomic exclusive locks. Now, if you want to have, let's say, two collections, which are the units of storage in MongoDB, like one for cart items and another for orders. And let's say that you point one to the other one by using the order ID or because it's going to be the same user ID, then modifications, changes to either side are not going to be atomic with respect to the other one. In other words, there's no concept of a transaction. And there's nothing you can do about it other than implementing transactions by yourself, which is something which is hard to do, and don't get me wrong, but you will probably get it wrong too, because it's very hard. So typically, this is why people rely on databases, because they provide abstractions for users, for developers, that you don't have to do by yourselves. But if you have to, it is very painful. And this is, of course, one of the most significant requests that MongoDB has. And there's no even roadmap yet for supporting any kind of transactions. So you're basically left with either without transactions or just putting everything inside the same document, which of course has a lot of trade-offs. The other significant problem is that there's no consistent reads on MongoDB. So the concept of a read in MongoDB, it is a little bit rigged. Basically, in MongoDB, a read operation that takes quite some time may yield to other processes in between. And when the access to the read is continued, when the read process continues to do progress, it may reacquire a different snapshot of the database. Well, there's no other way. So any changes that happen in between yielding that operation to other processes may appear on your read, which means that there are some effects, like you can read the same document twice in the course of a query. Or as you can see in the slide, this was a very recent post, so I'm not talking about ages ago. This still happens as of today, that someone found that in the context of heavy updates to MongoDB, when reading from an index, you can get many different results. So basically, imagine you have a collection with 1 million documents, and then you update continuously, but always keeping the number of documents consistent, so always 1 million documents. And then you read MongoDB, and sometimes you get 1,012,000, sometimes you get 900,000, blah, blah, blah. Sometimes you get really different numbers. Why? Because again, the reads are not consistent. And so you may read partially updated documents, not partially updated documents, but partially updated collection. So, if you want to see more details, you can read this post and figure out how this happens, but it actually happens. So this is also a problem if you, for example, want to run, let's say, a balance application, like a counting application in MongoDB. Your balance may not sum 0, and you have to overcome this at the application side. But probably the most compelling reason for MongoDB users to migrate to a relational database is for performing analytics. And if you ask MongoDB users, or if you yourselves are MongoDB users, I would ask the same question: how do aggregate queries, the analytical type of queries, work on MongoDB? I've never seen anyone who says they rock. Most of the people say they're slow, painfully slow, or undoable. And why is that? Because MongoDB is big data, right? It is web scale. We've been told that. So why is that slow for aggregate queries, for analytics, for data warehousing? The reason is based on the design of MongoDB specifically, but also in general for NoSQL. So let's look at this picture, for example. How do you think MongoDB perform an aggregate query? A collection scan, let's say. So a collection scan means that you're going to be scanning all the documents within the collection. And let's say you're going to have a query to aggregate on the salary, for example. You want to sum the salary by a company. So you do a sum, right, of all the salary information. Well, the issue is that if you look at here, MongoDB has this underscore ID, which is like the primary key. And then for each field, for each key value on the, let's say, JSON document, MongoDB stores 3 or 4 fields, which are the type of the value, the key, the name of the value, and then the value itself, and if the value is of variable length, the length. So the type of the value, the key, the length of the value optional, and the value itself. Now, MongoDB does not know, because this is NoSQL, which keys are present. So MongoDB does not know if this document has a key called salary. So it has to start scanning this document. cannot tell it apart from the rest. Then also it needs to scan the type because the salary might be a string, which you cannot sum. So it has to iterate document by document, and then key pair by key pair, analyzing all the fields and jumping over pointers just to check whether that key fulfills the query criteria. And then if it finds a match, that's okay. But if it doesn't, it still has to scan the whole thing. So basically, just answering any aggregate query typically means scan the whole database. If you think how this is done in a relational database like Postgres, for example, I'm talking about 8K pages because I like that for obvious reasons. Data is stored in columns, and those columns are defined in the table catalogs, and you know whether those columns exist or not, and which type they have or not. So even though you have to traverse some pointers, those are far easier, much more efficient to traverse. Needless to say, if you use a column store like CStore from Citus, then it's even easier because all the columns are perfectly aligned. And this type of queries, this type of aggregate queries, are even more performant, leaving aside the fact that it can be transparent compression in between, which requires then less I/O. But the most important thing is that in the end, if you are answering a type of aggregate query in the relational world where what is a collection in MongoDB is going to be split into several tables in the relational world, you may not need to scan the whole set of tables, maybe just one or two. To illustrate this, let me explain you an example. Let's imagine that you're developing a game application, right? And it is a very difficult game. So you just want to store basically who completed each level, and that's very difficult. So let's say there's only 1% of the people complete the most difficult levels. So you typically have a design where you have a table with all the players and then a table with the completed levels. This last table is going to be small because only few people complete those levels. So now when you answer an aggregate query over who completed the level, like for example, list all the players that completed the stage with more than 5 seconds left, then you only scan one of the tables, right? In this example, you would only need to scan this table, which is going to be small compared to the regular table. However, in MongoDB, all the information is going to be stored within the same document because you want a transactionality semantics for this information. So you have to scan the whole collection with all this information that you don't care about just to find information about the stages complete. However, again, if you would design this in a relational database, you would have two separate tables and you only would be scanning this, which means much less I/O and, of course, a faster query. And this is the main reason why analytics on MongoDB, it is very slow. It is not that MongoDB is terribly slow or not web scale. It is that it needs to scan everything. Whereas in a relational design, if properly done, of course, you would scan just a fraction of it. In order to prove this, we did a very nice test, which is, okay, let's craft an aggregate query. This is basically if you take the GitHub archive repository, which is it's an open data repository from GitHub that has all the events that happen on GitHub, and you take a subset of it. In this case, we took 1.4 gigabytes, which is not a lot. And then you craft a query, which is find the top 10 actors. Actor is an agent, is a user basically on GitHub. So which are the 10 users that perform the most events for the data that we have? And then we do this query in MongoDB, we transform the JSON documents into a set of relational tables and do the query on SQL and Postgres, and use a tool called IOTop to measure the amount of I/O required by the process, by the database to fulfill this query. If you do this in Postgres, you basically require 88 megabytes of I/O. Why? Because the tables you're referring to are not the whole set of the information that is available on the database if you do a proper design. However, if you do this to MongoDB, it requires 536 megabytes of I/O, which, by the way, it is exactly the size of the database when compressed. Because the original data set was 1.4, but MongoDB can use compression, And if you compress, this is exactly the size. So it means that MongoDB, it is effectively reading the whole database, which makes sense. There's no other way to fulfill this query without reading it all because you don't know what's in it. If I give you a MongoDB database, or any NoSQL database for that matter, and I ask you, tell me what's in here, how do you do it? There's no way to do it. Well, sure, look at documentation. Well, we all know how documentation is. So there's no way to explore data on NoSQL because there's no schema. If I give you a relational database, you'll look at the tables. It's very easy. But on NoSQL, there's no way to do it. So that's why many people, especially people that want to do analytics, but in general, all the people that like transactions or consistent reads, they want to migrate to MongoDB, to a relational database, mostly Postgres. So I hope up to this point you're more or less convinced of the needs for that. Now, how to do that? How to migrate? Because it's easier said than done. Well, the first problem is that we need to generate schema. So we have NoSQL, which looks a little bit like this. You know, a little bit of a mess because you can put anything in there. You don't even know the types. You know, the same column could be a string, can be an integer, can be a double, can be an array, can be a nested document. We don't know what's in there, so how do you generate the schema? Because we want something a little bit organized, something a little bit like this. So this is a problem. Even worse, MongoDB has a concept, they call it schemaless. I prefer to call it dynamic schema, which means that the schema of documents can change. So now let's say, okay, I found out that the information about person has a name, which is a string, and a surname that is a string, and an age that is an integer. Now someone just inserted a document where age is a string, because they say TBD, to be determined. It's very typical. So now my schema has changed. So even if it was already complex to infer the original schema from MongoDB, it's even worse if that can change over time, and it will change over time. So how do you deal with that? These are the two main problems in performing this kind of migrations. So let's look at the available tools in the market, specifically open source tools, but not only that. The first one is called MoSQL. MoSQL was developed by Stripe, the payments company from San Francisco. The idea was precisely this. Stripe was using MongoDB for fronting end their services, their payment services, but then for doing analytics, they migrate data to Postgres, and they perform analytics on Postgres. So how did they do this migration? They developed this custom tool called, again, MoSQL. It's open source. And so you specify the schema in a YAML file, and then it will generate the tables in Postgres and migrate the data from MongoDB, which means that only the fields that are on that YAML file will be transformed. So if new fields appear on your original MongoDB data source, they will not appear on your Postgres database. The problem, other than that, is that it's not inferring the schema. You have to know your schema. And if it changes, it won't be reflected. And also, development of MoSQL is stopped, and the tool is no longer maintained. And it doesn't support sharding. So, okay, can help a little bit, but probably is not the right tool for this job, at least as of today. We also have the foreign data wrappers in Postgres. The foreign data wrappers, probably you know, all of them know them. It is a technique to access external data as if it were tables in Postgres. This foreign data wrapper, now maintained by EnterpriseDB, was originally developed by Citus, and basically allows to connect to a MongoDB database from Postgres and map the resulting data as tables in Postgres. So, wow, this could be very compelling because I could just take the data and move it from there with a copy operation or any other tools that are available for SQL. The problem is that, again, we have to specify the schema. So it's as far as good as we specify the schema. And where do we specify the schema? When we create the foreign table definition. So it's flexible in how we can specify the schema, but the end result will be a single table where I would be flattening the fields in the original documents or not flattening them, or maybe I could create several tables, but it's all on my responsibility. And again, if the schema changes, if someone inserts a new document with just a new field, I will need to typically drop all these foreign table definitions, recreate them. This does not involve data movement, but this involves locking and involves any operation that I'm running, any running query may need to be stopped, canceled, or wait for it to finish before doing these operations. So, and there's no tool to extract the schema from the original MongoDB data source and import it into Postgres foreign table definitions. So there's work to do, and there is also some inconvenience, some shortcomings here. There's another foreign data wrapper developed by a company called Slam Data, which developed an analytics solution for MongoDB. And it's based on an engine they have called Quasar. So it's just another foreign data wrapper, which basically has more or less the same inconvenience in this case, which is, again, that you need to specify the schema, and if it ever changes, you need to reload all definitions, which may kill all queries, and so on. It is a little bit, in this regard, more advanced than the previous foreign data wrapper, but other than that, it doesn't give you a lot of power. There is the MongoDB BI connector. This is a proprietary solution by MongoDB and has two versions. Version 1, which is the one I'm talking about here, it is based on Postgres foreign data wrappers. I'm sure you know this, but yes, they developed the solution based on Postgres. So in order to offer their users connectivity to SQL tools, to the SQL ecosystem, to BI tools, well, you know, most BI tools cannot connect to MongoDB. They assume a relational database. They assume tables and columns. So they developed a bridge between these SQL tools and MongoDB, and version 1 used foreign data wrapper. It was developed by them. It is proprietary, but a prototype of that foreign data wrapper was published as open source, and it's available on GitHub. But as of today, even the proprietary solution shares the same shortcomings of these foreign data wrapper-based solutions, which is that you need to define beforehand the schema, so you cannot react to dynamic changes on it, and there's no way of mapping it naturally. And typically, all the solutions end up giving you a single table in Postgres. So if you want a nicely designed schema with relations, where arrays are, where typically MongoDB store collections of relations, like end-to-one relationships, then you would have to design this manually, and this would be very inconvenient, very difficult. And needless to say, in the case of this MongoDB BI connector, this is a proprietary solution, so you'll need to purchase the enterprise version of MongoDB in order to have this connector. And there's also specialized tools for data moving, ETL solutions. And these are okay, but again require a lot of manual coding or manual design to tell them how to grab this field from MongoDB to this column on Postgres or to this table in Postgres. So it's something you can do, but then it has another two inconveniences. The first one is, again, dynamic schema. Same thing, you'll need to redo your process. And second, they're typically batch-oriented. They're not going to bring your data live. As soon as something is inserted into MongoDB, it will not show up on your Postgres database. So how can you have a solution that will infer automatically the schema, which would be ideal, would be able to react to dynamic changes in the schema, and also replicate your data live, so you will have it instantly. And as soon as it appears in MongoDB, they will appear in your Postgres database as a nice set of tables, including relationships and everything you may expect from a relational design. So there's another open source project, which is the one that we've been developing so far. It is called TorDB Stampede, and it perfectly fulfills these three key characteristics of a tool that will help migrate to Postgres. So the way it works is it processes unstructured data in the form of a document, let's say JSON files, process them by an algorithm that analyzes the structure of these documents, and creates tables and relationships as necessary to match the input data. So let's say you have documents about books and their authors in JSON format. Once processed by ToorDB engine, it will look something like this. Authors separated by, and then books, relationships if necessary, and all the information nicely laid out in a relational fashion, as if a DBA would have designed the schema, with the difference that it's completely automatic. You don't need to design any schema. You don't need to create any table beforehand. Just start with an empty database, start running it, and you'll see all the tables created, populated automatically for you. So, how does it work? How does it infer the schema? That sounds very difficult. Well, actually, definitely it's not trivial, but it's not that difficult because the schema is there. So, what in the NoSQL world is schemaless, that doesn't exist. What is a schemaless? Schemaless means that there's no schema. If there's no schema, there's no structure. If there's no structure, how can you query data? That doesn't make sense. Rather than schemaless, there is some schema. It just is attached to the data. So when you look at the JSON document, what you're really shipping is the JSON document with its schema, so data and schema. That's why it can change from document to document, because it is attached to the document. So it's like DML and DDL at the same time. So we can infer that, because there's the DDL there. So what ToorDB does is extract that and infer the schema from the document. Here, name, address, these curly braces are the schema. So we extract it from there. So how does it work? This is a real example. So let's say you have this JSON document here. The way it will be converted by ToorDB to relational tables is very simple. So each level belongs to a different table. The names are taken from the database and the collection. Let's say MongoDB, this would be a database called ToorDB with a collection called people. So that will be a root table called ToorDB.people, schema ToorDB. So basically, database in MongoDB transforms to schemas in Postgres. And then the collection will take the root level, the root table. So here, there's some internal fields like the DID, which stands for document ID, or RID or SEG, which are also used internally. But then you have all the fields that are here. So name, there's name, the ID, there's the ID. And then an embedded document like address will result in a separate table. So if you have people, collection, address, then we'll have the table people address, where we have the fields street and number, right? And if there's an embedded collection, this collection will also turn into a separate table. In this case, an end-to-one relationship. So we have all the values here, let's say exploded or nested if you prefer. And this is, if you think about it, this is the way you would do this on a relational design. You would say, oh, a person can have many hobbies, so we'll do a relationship table. And all these tables, where all these columns are automatically done for you. There's nothing you have to do. No need to design any schema. Just start running ToorDB and it will be created for you. Even if new fields appear, it will be created automatically. So how do we react to these dynamic changes in the input data? So let's say we first receive a document with just the name, and then a new one appears with a surname. Well, we'll just do an alter table, add column. Columns are nullable, so this operation is almost free. And this is the resulting table. This is, by the way, an internal field of MongoDB. This is our own internal field, and then we have here the name and the surname. So the surname, as long as this column is nullable, on the first row, which, by the way, should be Alice, but I'm sure you get the point. This is null. And nulls are very cheap in Postgres. They're typically free, unless you have many columns, in which case it may cost you a few bytes. But this is not very high cost. So here you have, this is basically, if you think about it, what we do is create sparse tables with input data of varying columns. And what about type conflicts? What if you have surname here is a string and surname here is a number? Well, we don't want to destroy data, and we don't want to call as data to the most common ancestor type, which would again destroy type information. So what we do is very simple. The column names, if you just saw, have a suffix that indicates the type of that column. So if there is a data conflict, it's enough we will create two columns for the same type, same field, with different types. So it's very simple. The way this works, by the way ToraDB works, ToraDB Stampede to be more precise, it is connecting to MongoDB as a replica set, as a member of a replica set. So this is very unintrusive solution. So you have a MongoDB cluster, just add a new node to the cluster, to the replica set, and it will start replicating data in real time. It will perform this in two stages. In the first stage, it will do a base copy. It will copy all the information there. And when it is synchronized, it will start just replicating all the differential data, all the deltas in real time, or almost real time, basically following the same protocol as MongoDB does. So in other words, ToraDB becomes a secondary node of a MongoDB cluster. However, this replica will be transforming in real time all the information received as JSON documents into this set of relational tables. And from there, you can do your SQL queries, no problem. It is just a relational database. It is just Postgres there. So if you want to migrate someone from MongoDB to Postgres, the easiest way, in my opinion, would be to use this, again, open source tool, just connect it as a member of a secondary, as a new secondary of a MongoDB replica set. It will start replicating, it will start creating the tables, you will start feeding all the information into SQL, and then just connect to the Postgres underneath, and there you have it. You can keep it running there until the application has moved to real SQL, or if you just want to connect to the BI tools like Tableau or Pentaho or ClickView or whatever, there you have it. And you can keep it running live all the time if you want to. So you can either migrate people to Postgres or just leave them in Mongo, but provide them with this tool, a connector to the SQL ecosystem. Just a few notes about the architecture. ToraDB is designed in such a way that there's several abstraction layers, and as of today, we speak the Mongo protocol, and then we store data on a relational database. But thanks to these abstractions, in the future, we will be implementing other NoSQL protocols, to speak the protocols of other node databases, and we might also consider to support other storage engines, other relational databases as backends, other than Postgres. So basically, you can use this solution in several ways. One of them is to use it as what it's called in MongoDB terminology, a BI connector. So basically a tool to solve the mismatch between the NoSQL world and the SQL world, and be able to connect MongoDB, in this case indirectly through ToraDB Stampede, to tools in the SQL ecosystem, typically BI tools. In other words, typically for doing analytics or data warehousing. The other one, which is related to migration that we were talking about, is a data integration platform. So most of today's environments are heterogeneous. They have coexistence databases of different types. And you may have NoSQL and SQL databases in the same environment, but then performing aggregations of that data, it is not very simple. So if you say that you have data in Postgres and data in MongoDB, with this tool, you can bundle all the data together, even in the same database if you want. And then it would be very easy to query. The same for migrations. You can use this to migrate to Postgres, as we have described throughout all this talk. And more or less with the same idea, you can also write heterogeneous applications where you can just write some parts of the application with the MongoDB query API and let others do some parts of the other application with pure SQL, just querying data with SQL against this ToraDB server. So that sounds hopefully good enough, but what is the performance? Because I was telling at the beginning that the performance of MongoDB for doing this kind of aggregate queries was not ideal. but how bad it is, or how good it is, this other solution, so that could be a compelling alternative. So we have performed many benchmarks based on open data, and we basically, I'm going to show you here some data from this GitHub archive, which is independent source of information from GitHub, and we compared basically three things: a MongoDB server, a MongoDB cluster with 3 shards, so the query is distributed among 3 nodes, and the same query done with SQL against the PostgreSQL database generated by ToraDB Stampede. Here we have just tried with 6 queries. There's much more available in our blog, and the queries themselves are here on these gists, so you can check the equivalent query in SQL, the equivalent query in the MongoDB API. You can also see there which one is more complex. I can advance to you that queries in SQL are far more readable, even though you're not used to SQL, which I'm sure you all are. So even better in those cases. And here's the results. So even for tiny data sets, the differences are really surprising. So typically, performing the same query in SQL results in numbers that are even 57 times faster than a single MongoDB database, or significantly faster than a shard of 3 nodes in MongoDB. And put your numbers. Even if we take a 10 nodes MongoDB cluster, the numbers would still be significantly faster. And this is small data sets. With larger data sets, the numbers are even more different, more significant differences. And we don't know this. I mean, the relational databases like Postgres with SQL are pretty good at doing this type of queries. Whereas MongoDB and most NoSQL databases, because of the architectural problems I explained before, have these limitations in terms of performing aggregate queries. They're really good or really fast for accessing data based on an index, typically by primary key, typically in MongoDB by ID. But aggregate queries are a different beast. So this is one of the benchmarks that I can show to you. If we take an even smaller data set, because in this case, most of the data in Postgres is residing in memory, whereas in MongoDB is not, of the queries we can do, the difference is even more significant. We're talking about almost 300 times faster. It's not 300% more. We're saying 300 times faster. Queries that run in many minutes or hours take a few seconds in Postgres. So the difference is really significant. I mean, in this case, query MongoDB is taking 20 minutes and only 9 seconds in Postgres. It's a really significant difference. That's why analytics on MongoDB, it is very difficult. Some people say, hey, but you're not using indexes there. Well, typically indexes are not used on aggregate queries. Sometimes in some operations, maybe for sorting operations, they can be used, but not always. But what about if we turn indexes? By the way, in ToraDB Stampede, you don't need to define the indexes. The indexes that you define in MongoDB will be replicated to the equivalent indexes in relational. You don't need to do anything. But what if we turn them on? What if we create specific indexes on the specific queries that we are doing, which of course is not very realistic, specifically if you're connecting to a BI tool where you don't know what queries are going to be doing, and you're not going to be creating, of course, hundreds of indexes. But anyway, in order to prove that point, the difference is still very significant. We're talking now about 94 times faster. It really doesn't matter. We're just 2 orders of magnitude faster. So let's standardize. It's just 100 times faster, and that's it. Doesn't really matter whether it's 80 or 200. So that's pretty much it. Let's see if we have some minutes for a demo, which, as demos happen, always fail, but let's see if it doesn't in this case. Before doing that, any questions so far? Yes?
How you write the queries equivalent to MongoDB query?
So the way you write these queries, it's of course SQL dependent, right? And it's based on the layout generated by the tables by ToraDB. And typically, they look like relationships, right? So typical queries, and you can see if you go to our blog site, you'll see these benchmarks explained in much more detail, and you can see the queries in MongoDB and the queries in SQL, and you can compare. You'll see the queries in SQL look very natural, because the tables are a little bit like if you would have manually designed the schema.
I ask about table names and column names.
So the table names, I'm going to do the demo too right now, you can see. But as you can see from the previous slides, the table names are generated. So there's a consistent algorithm for generating table names. So first of all, a database in MongoDB maps to a schema in Postgres. Then each document, the data that is on the root level, in this case, name, ID, and well, address and hobbies are going to rely on a separate table. But name and ID are going to be the root table, the root level for this document. And the root level will be contained on the table with that collection name. In other words, in ToraDB.people. Then if there's a nested document called address, it will be an people_address. And so forth.
And what about suffix, suffix?
The suffix, okay. By the way, there's an error here. This should be people_hobbies. And then the suffix of the column names, they are fixed based on the data type. So for example, S is a string, I is integer, and so forth. And this is documented. And then of course, if you don't like that, you're free to create a view. So create a view, rename fields, drop fields, coalesce data, types, it's really up to you. There's also, ToraDB generates some internal catalog information, metadata, under the ToraDB schema, _ToraDB schema, and you can query that to infer which tables have been generated, which databases have been propagated from MongoDB, which column names you have, which types are available, all that is in the catalog metatables of ToraDB.
Thank you.
Does ToraDB generate indexes or foreign keys, something like constraints?
Okay, so question is whether ToraDB generates indexes, constraints, foreign keys. Indexes, it generates two types of indexes. One are internal indexes that are used just internally. Like for example, this DID, which stands for document ID, is like our internal primary key, and that is an index. Also, the indexes that are created in MongoDB will be propagated as indexes in ToraDB. However, one index in MongoDB may mean one or more indexes in tables in Postgres. That will be done automatically and will be on the same fields that are required. Foreign keys, we disable them actually because typically all the data that you have there, it comes from an original data source. It needs not to be validated. There's no need to basically check whether it fulfills a given constraint. And insertion time was penalized by that. So we removed those, although technically speaking, there are foreign keys. You know, when you talk between the relationship of hobbies and people, first of all, there's the DID. That is a foreign key. So on the hobbies table and also on the address table, the DID is a foreign key to people, although it's not specifically used as a foreign key internally because it's all machine generated. We don't need to perform any validation.
What about duplicates? For example, if hobbies have the same values for every people, for example, for Aries, for Bob, for other people, what about table ToraDB point hobbies will grow continuously, or it will contain only unique values? For example, reading once, talking to release once, or repeat for every person.
That is a very good question. So the question is, let's say this table hobbies is supposed to contain a limited set of values, right? And so they are repeated all the time. So in a pure normalized design, you would typically put a restriction on data with a foreign key and say, you know, the values need to be contained on this lookup table, which would be another external table. Well, we don't want to go that far. even though we could technically speaking. So all the values would be duplicated in the hobbies table, because what we want here is to reflect the same data that you have in MongoDB. If we would start fiddling with that, it will be a different thing. Now, of course, if you're going to migrate, this is something you may want to do afterwards. And it wouldn't be difficult. Once you have that, you can craft a query to select the distinct values, put it on an external table, then create the foreign key. The good thing is that on top of this, you can create views, you can create all the tables, you can create materialized views. It's all up to you in order to do that.
So, as a host of this auditorium, I should tell that we have 5 minutes left. So probably we can leave questions for just outside. And if you have time for your demo, please show it.
Thank you.
Thank you.
Yes, I'll be doing it very quickly. It is very quick itself. So hope you can see the font size. So TorDB, you can go to our website, which is, I'm not connected, yes. So go to tordb.com, Stampede, tordb.com. Well, you download a tar file from there. It's very simple. By the way, TorDB is programmed in Java, so you require a Java virtual machine to run it. So let's assume you just go to the website and download the tar file. It should be here. Yeah. So let's assume you have downloaded that already. So let's untar that. And now, TorDB Stampede, as I mentioned before, assumes that you're going to be connecting to a MongoDB replica set. So you have to have a MongoDB replica set. Here I have a MongoDB already running in replica set. So this, I'm connecting here to the MongoDB primary, running against MongoDB 3.2 in this case. And it will have some data, but I'll import some data afterwards. So now TorDB is here. In order to run it, I'll just say TorDB. And then I would pass a config file. You just need a config file to run it. However, if you just do a -l, this will generate a sample config file. It is in YAML format, which you can just redirect to a file and edit it. This is one option. But TorDB is also designed in such a way that if you would use some tiny conventions, you will need not a config file to run it. So it's even simpler. So for the purpose of this demo, I mean, if you want to really configure it and tune it down, just generate the sample file with tordb-l and get your sample config file, and then you can edit this config file, right? But if you wanna, and then there's all documentation about how to tune this file, but it's not very difficult. But let's follow these conventions for now. These conventions are that I have a MongoDB running on localhost with a replica set called rs1, which is the default name for MongoDB, that I have Postgres running on localhost, that this Postgres has a database called ToroD, which I'm going to create right now, and that is owned, I forgot that it's owned by a user called ToroDB, so let's drop it. All right, so I'm just following these conventions. As you can see, it's an empty database right now. And that this user is able to connect with password. So I set up a file called ToroPass, which contains users and passwords in the PGPass format to connect to this database. So if I follow these conventions, which I need not to, only if you don't want to edit the file. But if I follow these conventions, I can just right now, I have a screen here, yes. So I can just run TorDB without any config file, without any further options, and it should start running. Okay, typical for demo. So, Let me do something. So let's launch again. I'm not seeing the error. Oh, must be owner of. Hold on, I'm just thinking. Yeah, that is, I'm sorry, that's a very old version of TourDB I was using there. Let me see if I have. Oh, here, there it is. Okay, so sorry for that. I was just using a very old version of TourDB. So let's start the correct version. Downloads TourDB Stampede. Yeah, that looks better. All right, so again, the same thing. I would do TourDB Stampede. Let's drop the database again. Recreate it again. So again, I'm restarting the demo, starting from an empty database, following these conventions. So now I can just say, I'll do it on the screen, it's going to be better. I'll launch TourDB Stampede. Okay, so now it's booting up. In this process of booting up, it's starting the replication process. It's already connecting to MongoDB, detecting all the information available in MongoDB, and you see now it's creating indexes, tables, and so on. So while this completes, because there is some data on the MongoDB, let me just connect to this database, TourD, and notice that there's already a lot of data there. Remember that I just created this collection from scratch, this database from scratch. It's already 100 megabytes here, and I have here, again, some data that has been created by previous data that I had on MongoDB, and it's all here. So right now, by the way, it is stop recovery mode, so TourDB Stampede first boot up in recovery mode, which means it will copy all the data, and then we'll start secondary mode, which means everything that I insert into MongoDB will come here instantly. So in order just to finish this, let me just quickly insert something on MongoDB. Let's do a Mongo import. Here I have some demo data. So let's call pgconf root. So I'm just going to import 10,000 documents for the purpose of this demo on a database called pgconf.ru, on a schema called pgconf.ru. If I look at the logs, there's here already some logs about pgconf.ru. If I now connect to the database, there's a schema called pgconf.ru, and if I list the tables there, there's already some tables there which represent all the data that I have just imported. So you can see it's real time. Everything that I insert there gets inserted here.
So it's time, and thank you, Alvaro.
Thank you.
Thank you. Applause. Unfortunately, we don't have any more time for questions, so you can just meet Alvaro anywhere else. Thank you.